Okay, now let's think about the problem about having more than two variables. So basically, if we only want to calculate those coefficients, then there's nothing more special. Suppose we have more than one independent variable, okay, and we want to use all of them to explain our single dependent variable. Okay, for example, to use to use size and the number of bedrooms to predict or to estimate the price of a house. Okay, if we want to do that, now what we are doing is called linear multiple regression, like this. Okay, yi will be a function of beta 0 plus beta 1 x1i plus beta 2 x2i plus epsilon i. Yi again is the house price. x1i is now the house size of house I. x2i is the number of bedrooms of house I. Okay, all of these are of house I. And finally, epsilon I is the random noise of house I. So nothing special. Now we simply have one more term, and we relabel x for house size to x1 because now we have two independent variables. If we want to calculate beta 0, beta 1, and beta 2, we still have a closed form formula. Again, we don't really care about that formula because we have R or Excel. Now we need three vectors, and when we call LM, the formula would be to use size and bedroom to predict price. Okay, this plus sign is telling R that I want to study a linear relationship between size and bedrooms. Okay, I will do beta 1 times size plus beta 2 times bedrooms. Anyway, it's the grammar of R. And once you do this, immediately you see the coefficients. Okay, you will see that our estimate for beta 0, beta 1, and beta 2 will be around 82, 2.8, and negative 15.7. Okay, that will be our estimation about the three parameters. If you want to use Excel, basically it's the same thing. The data is still here. The only difference is that when we want to set up our X range, now we need to include both columns. Okay, all others are the same. And once we click OK, we will get the three estimates. Okay, so it's just as simple as doing a simple linear regression. And then we have our solution. This is our regression model. Again, whenever we get the outcome, we need to somehow try to interpret it. Okay, and here let's try to do that. Now we will see that whenever the house size increases by 1 meter square, we expect the price to increase by around 2,800. Okay, this number is greater than 2,100. The coefficient that when we only have one independent variable. Okay, so you can see that whenever we have another variable, that may affect the coefficient for the original variable. Okay, kind of reasonable. And then what's more interesting is that we now see that whenever there is one more bedroom, we expect the price to decrease by around 16,000. Okay, so now this may or may not be surprising to you. Okay, if we have a house, basically we somewhat should we someone should expect that the number of bedrooms is good news, right? We expect to have more bedrooms. Having 2 bedrooms should be better than having 1 bedroom. But it may also have a negative effect. If our house size is limited, it's the same, it's fixed, then having more bedrooms may result in small bedrooms or small spaces for other kinds of rooms. Okay, so we cannot really say that there is a definite relationship between number of bedrooms and the value of that house. Okay, for different people, they may have different perceptions. For different houses, for different sizes, they may have different impacts. So when we see this result, we actually should be very careful. This result may actually come from a somewhat wrong assumption. Okay, at the beginning, we assume that there is a linear relationship between all the variables. We assume that how the number of bedrooms affects the price of the house is linear. But if we think about it more thoroughly, it may be, for example, nonlinear, right? When you have no bedroom, having 1 more is good. Having 1 additional more is good. But when you already have 2 bedrooms, then having 3, 4, 5, 6, 7, 8, 9, 10, at some certain point, the value of that house is going to decrease when you have 1 more bedroom. So we probably should not say that the number of bedrooms and the price has a linear relationship. And if this assumption itself is wrong, then of course this coefficient is not going to be so meaningful. Okay, so whenever we get the regression output, we need to interpret the result and determine whether that result is meaningful by ourselves. Okay, this is always what we as decision makers need to do. Calculating these numbers can be done by the software, but we need to decide whether we want to do this and whether this result is meaningful or useful. That's what's most important about multiple regression. When we have more than 1 independent variable, we need to be careful about what's going to be important, what's going to be meaningful in this model. Anyway, let's try to conclude this section. So we now can say that the number of bedrooms may not be a good indicator of house prices after the thorough investigation about this relationship. So that means, in general, we should have a way to test whether these coefficients are really, in some sense, significant. Okay, whether these impacts are really some impacts. Okay, whether they really have some impacts on the price. Okay, we want to test those significance. And also we want to judge the overall quality of a given linear regression model. For example, for predicting the value of this house, we have 2 models. We have 1 model with only size as the independent variable. We have another model with 2 variables with size and the number of bedrooms. In many cases, we will have multiple regression models, and we need to decide which one is the best. In some sense, it's the best. Okay? In the next video, we tell you how to define the best one. Thank you.